main reason we're here is to talk about Lemonade and all the cool stuff you could do within Ubuntu. But before we get to Lemonade, I want to talk about some of the background that's gone into Ubuntu 26.04 that makes a foundational experience for Lemonade to be great. I think go through your background.
Ken VanDine. I've been involved with Ubuntu Desktop now for almost 2 decades. It's been quite a ride. But my recent addiction has been Lemonade and local inference on device. So very excited to be involved.
Okay, so let me start with my background so you can understand the types of work that I do in open source world and why I worked on some of the things I did for making Lemonade on Ubuntu a great experience. So I've been working in Linux in some capacity for about the past 18 years. I spent a large chunk of that time at Dell and the past 5 years working at AMD. At AMD, I'm part of the client Linux team that works on everything involved with making client hardware work well. Our team works both on AMD's reference designs as well as OEM designs to make sure that all the things that are necessary to certify the hardware happen and so that it can be certified with Ubuntu. I personally work on a variety of open source communities. In the kernel, I'm a maintainer for the AMD pstate driver and the AMD HFI driver. These core drivers are used both for managing the CPU performance as well as the power consumption. I contribute to any driver or subsystem that I find a problem, though, in the kernel. You'll find my name in commit logs for pretty much all of the AMD drivers, but I do work in cross-vendor solutions like PCI and ACPI. In user space, I'm one of the maintainers for the upstream fwupd project. Richard Hughes and I have been working on this since the early aughts. It's ballooned in significance. The project started with flashing some enthusiast hardware, but now it's morphed into flashing mission-critical hardware for OEMs across the world. It's a key tenet to the security story for vendors that support Linux. We now have support for about 150 flashing protocols and thousands of different types of devices. The number of downloads have grown so astronomically that it's measured in the hundreds of millions. Besides those upstream projects, I'm also a Debian developer. I'm also a Ubuntu Core developer. And because of my background working upstream on fwupd, one of the most important things I maintain is that fwupd stack in Debian and Ubuntu. In Debian the past year, I spent the time that I had with the Debian AI team as it pertained to packaging. But as I have lots of other hats and responsibilities, I do what I can. In Ubuntu, I work on whatever issues come up. I'm not afraid to touch systemd, GDM, Mesa, whatever it is. If there's a problem, I'll fix it. I work on upstream solutions, and I bring them back down to Ubuntu whenever I can. Okay, so as AI has exploded across all walks of life this last year, the best and most performant solutions require data center class hardware. Every time you use Claude, Copilot, that kind of software, you're spinning up cycles on a data center GPU somewhere. But there's actually a lot of models and a lot of solutions that can provide a good enough performance with consumer-grade hardware. And that'll let you keep all the inference local. You could save some money on tokens. You could build some really cool solutions with it. This could be done with consumer discrete GPUs, but the limiting factor actually ends up being the amount of VRAM in the GPU. Usually the biggest ones are 32 gigs or so. This is relevant for the latency of traversing CPU memory versus dGPU memory. It's orders of magnitude difference. But that all changes once you have a high-performance APU system. An APU is a system-on-chip design where you have the integrated GPU that can access all the exact same memory that the CPU can access. And so in the last calendar year, AMD released Strix-Halo into the industry. This can be configured with 128 gigs of memory. It's got 40 compute units, 256 for bandwidth, and 16 CPU cores. Performance on it is phenomenal. There's designs from a variety of OEMs, comes both desktops and laptop form factors. I use it for my work laptop personally, and I've been loving it since I switched. Since it's come to the market, we've had a lot of time on improving the experience for all layers of software in the stack. Ubuntu 24.04 or 26.04 showcases some of those, and I want to walk through some of the specific things that we did. So APU systems have something called a unified memory architecture, which means the exact same memory chips can be utilized by different devices within the SoC. So that's why APUs are so great. If you have 128 gigs of memory, that means GPU, CPU, NPU, they can all access the exact same memory space. For security reasons, we have something called the IOMMU, and its role is to translate virtual memory access into a physical region. That becomes important because when you have untrusted devices, like a USB 4 has exposed a PCIe port, you can potentially do a DMA attack on the machine. You don't want someone plugging in a malicious device being able to access any of that sensitive stuff that you've been doing inference workloads on. So because of the approach to security, it's going to mean that when you create a page table entry for the GPU, you go to the IOMMU and you have to do a translation. And there's going to be some small performance overhead from that translation. If you want to avoid that translation, what you could do is instead have a predefined region that's exclusive for GPU use. And so this is what AMD calls variable graphics memory. The size of the region is flexible. It could be as small as 512 megs or as big as 64 gigs. The reason it can't be 0 is because that region is also what's used for the frame buffer before the OS would load AMD GPU. It's the same thing that you use to show the BIOS logo, the Ubuntu splash screen, all those kinds of things before you get to GDM. Okay, so this variable graphics option, it's exposed in BIOS menus, but BIOS menus aren't always the most user-friendly place to change the settings. So we worked out a solution that allows changing the BIOS options from Linux. The way it works is that we have an ACPI interface that AMD GPU can query the current BIOS configuration option for variable graphics memory, and another one for setting it. One of my colleagues worked on the AMD GPU stack that talks to the interface, and when you're in a supported system, the driver will detect it, query the ACPI interface, and populate sysfs files. Writing them will update the value for the next boot. But so since this has implications on what happens to the system on the next boot, only root can actually write it by default. But you know how I mentioned that we work on fwupd? Well, there's a cool feature fwupd has that I wrote a few years ago. When the kernel exports a BIOS setting, it can parse those BIOS settings by the daemon and present them over dbus for any fwupd client to actually read and modify. And the main reason for this is to do things like turning on secure boot or changing the boot order, usually security sensitive things, but the sky is really the limit here based on what the OEM actually wants to support. So I decided to plug in our new AMD GPU interface into the fwupd BIOS settings infrastructure. The net result is that now you can use any fwupd client that supports BIOS settings to read the current value and set a new value. On the slide here, you could see how it works with the fwupd manager command line tool. This is from Ubuntu 26.04 on a Strix laptop. I think there's a lot of opportunity here for other clients to do the same thing. I'd love to see something like this land in GNOME Control Center, KDE Discover, all these kinds of tools. They can all have something very similar. Okay, so let me move over to ROCm now. ROCm is AMD's comprehensive stack of AI tools and libraries that can be used for any application inference. AMD started to do ROCm support for consumer hardware over the past few years, but it relied upon AMD's built and provided binary packages. As you probably heard from Corey a few years ago at the Ubuntu Summit, there's an effort to build and support ROCm and Debian. That work's still ongoing, and due to some challenges with how long the new queue was taking and package reviews in Debian, it got stalled quite a bit. But for Ubuntu Resolute, Canonical and AMD worked together to package the entire ROCm stack and to also build some popular software against that stack. It's been an incredibly difficult undertaking because the ROCm stack is built with the HIP compiler. It required bootstrapping a brand new unique compiler stack. There had to be decisions about which ISAs you want to support. There had to be strategies employed for how we would build the packages differently in Ubuntu versus what AMD was building on AMD infrastructure. And quite notably, it exposed some unique build bugs at the time. One of the toughest things that we had to work through was build delimitations, because some of the link operations require so much memory that the build Ds would kill the jobs or the jobs would time out. I'm really proud of what AMD and Canonical did together to build the entire stack. As mentioned earlier, today, if you take a Resolute install, you can do sudo apt install ROCm. You get the runtime, the math libraries, developer tools, everything you really need to build software against ROCm. But for an end user, non-developer, that isn't really what you want. You want AI software that utilizes ROCm. You want something that runs measurably better with GPU offload than it does with CPU offload. And so that brings us over to Lemonade. If you go and visit the Lemonade website, you're going to see the tagline. It's the Omni-model alternative to cloud AI, automatically optimized for your GPU and NPU, open source, community-driven, and private. And so this has gone through quite the transformation over the past year. It was originally conceived as a tool specifically for evaluating LLM performance. It was Python fast API wrapper, and it was wrapping Llama CPP. But as the Lemonade team has continued to iterate, the design switched to C++. It's grown support for more backends beside Llama CPP. It's got Ollama API support, so any apps that talk to Ollama could talk to Lemonade also. It's gained support to broadcast OpenAI compatible APIs to other software. This all goes to say that there's been an immense amount of development on Lemonade, and the Lemonade you see today might look quite different than Lemonade does a year from now. And so when I first got involved with the Lemonade project, it was distributed as a CPAC-built Debian package. The codebase had cases where it would go and do things like scrape the output of LSPCI to identify hardware. It had hard code assumptions about how the app was built using Node.js repos from NPM that didn't really translate over to a buildy environment. At runtime, it would only download executable content from GitHub. It didn't really have any sort of confinement or security. So I took it upon myself when I joined the Lemonade community to improve everything I could to get the package into better shape, to be natively packaged in Ubuntu and more friendly for the average Linux user. One of the first things I did was I got rid of the Electron dependency. And, the Electron could be great. I mean, it's why we have VS Code. We have all this other software that runs on Ubuntu. But in this case, it's basically a React.js app. Doesn't really need the Electron APIs. So I added an emulation layer into the server, and now the server is set up that I can serve the Lemonade front end directly to a browser. Once I had that working, I was able to get React.js app built without any node repositories. There was a few ITPs that had to go along the way. Did those with Debian, sync them to Ubuntu. Some upstream changes on the decision of dependencies, eventually some flags in the build system for how it works. But everything now is upstream, and the Debian packaging is very straightforward. The next big thing that I did was I added support for systemd. Lemonade runs as a server process, but doesn't really act like a traditional Linux daemon. As a user, you would launch the server process, which I thought was weird, and especially dangerous since Lemonade was pulling GitHub artifacts from the web. So I did modifications for the server to let it run in a confined systemd unit, its own user process, only access to certain directories. It can still reach the web to get artifacts, but something bad happens, it's going to be a much lower blast radius. After this base level work was done, I tied all this back together with the inbox ROCm packaging work. And so I now added what we call the system Llama CPP backend. As I mentioned before, Lemonade by default pulls those artifacts from GitHub, which is great to get up and running quickly. But if you want to avoid running untrusted code, that's not going to be optimized for your hardware. It might not be great. So we worked on getting Llama CPP and GGML libraries into Universe and building them against that inbox ROCm stack. We tied that all together with the system backend. And so now when you install Lemonade from the app repositories, it'll check whether or not the system has Llama server on the path and if there's a ROCm stack installed. If it's installed, it will use that rather than going to the web for more artifacts. To make it even better, it's all tied together with recommends. So if you go and do sudo apt install Lemonade server, it's going to pull down Lemonade, Llama CPP, GGML, all the libraries you need for ROCm. You're just a few minutes away from running any of the models through the Lemonade web interface or any software that talks to Lemonade. All of that model execution is contained in the Lemonade systemd service. But so with all this great work and all the great hardware, you can get a chat interface in the Lemonade front end. It's multimodal. You can work with text, speech, and images. Uses GPU to run an inference. That's just the tip of the iceberg. And so I'm going to hand you off to Ken now. He's going to show you some of the really cool things that he's managed to build on top of Lemonade. Okay.
All right. Cool. Yep. So what else? So I get to do the fun part here. I can show off some of the my cool addiction for the last 6 months. So about 6 months ago, I got my hands on a fancy framework desktop, Strix Halo machine, and I could not help myself but to try to exercise that thing as much as I could. So I've got a few demos here that I will share.
It wasn't clicking. I had to click the thing manually. Oh, that's well.
All right, so it's a video. I may play it a couple times. This is basically the desktop app, which looks exactly the same as the embedded web interface, which is kind of cool. If you just go to the right port number and the server's running without the desktop app installed, you will get this exact same view. But this is a basic chat interface that you would expect from anything, right? It's not super exciting, but it is a way that you can interact with your local environment using Lemonade. And in this case, it's using a Quinn model running Llama CPP, of course, in the background. But one interesting thing about this is, well, actually, I want to get back to what Diego teased earlier about the name. No, Lemonade is not named after Mario, Limonciello. The name Lemonade comes from, and it's actually, naming is hard in software, right? But this is actually kind of cool. It's an aid for running your LLMs. It's an LLM aid. That's where the name Lemonade comes from. I had nothing to do with the name, but I do think it's kind of cool. This is another example of the same UI, but in this case, it's using a stable diffusion model, so it'll generate images. So I selected a stable diffusion model, and it knows now, changes the UI so you can generate images. Also not super exciting, but it's a way to kind of exercise it. And this is a little bit cooler. The next one is that I will explain further. I gotta wait for it to finish playing. Okay. Explain a little bit further in a later demo. But we have this concept of an Omni-model, where you can load like a collection of models that are capable. So there'll be like a text and visual model, a stable diffusion model, text to speech and speech to text model all get loaded, and they can talk to each other, which is super cool, right? So in this case, I chose that model, and when I type in a prompt, it knows my prompt was asking for an image, so it created an image. But that's using the Omni-model concept. I have a better example of something that's in the works right now in a future slide. All right, now this is kind of cool. This is super cool, actually. So Actboard, I get no credit for this. Krishna from AMD did this. He's also a Lemonade developer. But as developers, we have many places where we have to pay attention to, Discord comments and GitHub PRs, Reddit posts, lots of places where we want to interact with our community. So he created a board that will go out and find all the information that you might want to read, decide if it's something you should act on, if you should just monitor it, or has somebody else already handled it. So if there's an interesting topic for you on Discord, and then somebody else has already responded to it, it'll flag it as handled. So I see that, oh, somebody's already taken care of this, I don't need to do anything. But if there's something that I should act on, I can click on it, it'll take me to Discord and let me see exactly that message, and I can respond to somebody. The one thing I did here is, you see here, there's some LP. I did add some Launchpad integration for the Ubuntu sponsorship page. So I can see when there's packages that I'm interested in maybe sponsoring for people, when there is something in the queue for me that I could help with. But this is a super cool feature. I love this thing, and it also publishes to a Notion dashboard. So on my phone, I can see it as well. And in the Notion dashboard, it will pre-populate potential replies. So I can just copy what it drafted for me and just post it on Discord. It's super cool. So that's running a series of agents running on my Strix Halo machine at home. Super cool.
That's super tuned to you specifically, the things that you like to respond to.
The types of things I like to look at. Now, this is automated Ken. This is something I am really excited about, and this is something I've been hacking on for a while. But this is a dashboard of all the snaps that I maintain. So I have another addiction, if you can't tell. I maintain a lot of snaps. And historically, what I've done is I've had lots of automation on GitHub that would go out and look for a new release of a snap, parse the releases JSON file, do a set in my YAML, push it to GitHub, trigger a build, all kind of, it can be fragile, right? So now I have agents to do this. So in automated Ken, I can plug in my publisher name, my GitHub account, and I have a separate bot account for GitHub, so it can create PRs for me without touching my normal stuff. And it goes out and just runs. I have agents running on it, and there's agents that look for updates. There's agents that trigger tests. I have some test suites that use YARF to capture screenshots and uses a model on my Strix Halo machine that does a visual comparison to say this is probably broken or probably not. And there's like a 91% threshold I think I set. And if it passes, it will automatically promote my snap. This is not complete yet. Like, I have some of my snaps, the entire flow working. And one very interesting thing I discovered with this is my agents are super smart. The agent that goes out and checks for a new version, the version bumper agent, I had one of my snaps that repackaged a deb binary into a snap. The upstream in a new release released it only as a tarball. It figured out that, changed the Snapcraft YAML, and the PR that it submitted worked. Like, it repacked the new tarball in the right paths, and it submitted a PR that worked. It was great. So one of my plans for this summer is to finish building out all my test suites for all my, I think, 81 snaps I maintain now. So I have reliable tests beginning to end to make my life easier. But I think this is super cool. I'm also going to work to make this a bit more generic so some other people could try to use it. Right now, it's got a lot of assumptions to me because the idea was it was making my life easier. But I think this is super fun.
I think because it's a video, you got to wait for the video to finish or something.
Oh, yeah. I thought the video would have been done by now. All right. Now, this is the other thing I mentioned earlier with the Omni-model. This is a work in progress RPG that's being created by Jeremy Fowers. He's the lead developer of Lemonade. He's working on this right now. It's not done. This is just a screenshot as of yesterday. But this is leveraging the Omni-model capability where there's a single API endpoint that loads an Omni-model. And it is a role-play game where as you respond to it, it generates prompts that not only gives you the next step, but also generates a related image and displays that image. So the Llama CPP side talks to there's a tool call into Stable Diffusion, generates an image, and populates this. So this is a game he's working on. You can see it's very on brand for AMD right now. Halo Tales, Halo. But this is kind of cool. But this is really a great example of how this sort of thing can work. And there's audio built in as well. I haven't actually witnessed this myself because I haven't had access to the code, but it leverages the text-to-speech, speech-to-text stuff as well. So, and that's it.